Okay, for example 9, we've got a couple of slight differences. The first difference is they give you the initial velocity as a vector. So that shows that it's resolved straight away into the two components, right? Because if you know that this line here is 5i plus 8j, we can think of that as the two different components. We know it's 5 across, and we know that it's 8 going up. So actually, we know the initial velocity to the right is 5, and the initial velocity going up is 8. It gives us a diagram as well, which is really nice. So we don't have to draw our own diagram. We see we're 2 meters off the floor, and we can see that it asks for the greatest height above the ground reached by the ball. So I've marked this on the diagram. There's the turning point here, and we know when something is at its greatest height is when the velocity is turning. It's turning from positive to negative in the vertical direction. So we're going to use that to get the answer to part A. So if we start off by taking the fact that when we do it in the vertical direction, you've got that V is equal to 0. You've taken up as positive, so A is minus 9.8 from the gravity. U is 8 from my diagram here, showing the 8j going up. And we're looking for the greatest height, so that's S. So when we do that, we put it into the appropriate formula. It's going to be V squared equals U squared plus 2AS. We get 0 equals 8 squared plus 2 times minus 9.8s. This is then 64 minus 19.6s. And then we rearrange and divide, so S is 64 divided by 19.46. So it's 3.27 meters to 3 significant figures. The more observant of you might have noticed that I've underlined this line here, above the ground, right? Because actually what we've got is not an answer to the question, right? This is the greatest height above the ground they've asked us to find. What we've found is the greatest height above the starting point. Remember, S is always the displacement from where you start. So we started at A, so we're 3.27 meters above A, but A is 2 meters above the ground. So to find the total above ground, right, we're going to do 2 plus 3.27, which is 5.27 meters to 3 significant figures. Remember, I always round to 3 significant figures because that's what the mechanics paper asks me to do. Part B asks us to find the speed of the ball as it reaches B. Right, so if we're looking at B here and we need to know the speed, well, the speed is always the magnitude of the velocity. So what I need to do is work out the velocity as we reach B of both horizontal and vertical components, and then I can use my Pythagoras to find the magnitude of that velocity and therefore get the speed. So we need to resolve in both directions. Let's start off, doesn't really matter, we know we've got to do both, so I'll start off with the horizontal. And in the horizontal direction, we've got that U equals 5, we've got A equals 0, but then we've not actually got any more information. So there's a couple of things we can do. If we really want to use Suvat, we could go and find the time from B. So you could work out the time from the vertical component. What time does it hit the ground when it's 2 meters below, and then substitute it in. But think about what we've got. The initial velocity is 5 meters per second, and there's no acceleration. If there's no acceleration, the velocity won't change. And we said this right at the start. Any horizontal movement is going to remain for the whole time. So the velocity in the horizontal distance when we're at point B is still going to be 5. V equals 5. So that's the horizontal one done straight away as a trivial solution. When we do it vertically though, we need to work a little bit harder than that, right? But we know all the key things. We've got U is 8. Diagram over here shows it going up at 8 straight away. A is minus 9.8. We know that S, well, it's 2 meters below where we started point B, so that means that S is minus 2. This is taking the positive direction as up and the down direction as negative. And that's enough information because we need to find V, so we can use our formula, which is just going to be V squared equals U squared plus 2AS. So V squared is 8 squared plus 2 times minus 9.8 times minus 2. Pop that into the calculator and we should find out that we get a value of 103 0.2 for v squared. Then when we square root that on our calculator, we will get 10.159. Now we've just square rooted, so we have to take positive and negative square root. If it was time, we'd discard the negative answer, but this isn't time, this is velocity, and velocity can be negative. So let's have a little bit think deeper about what's going on. Well, we're travelling down at this point, so if we're travelling down, then the velocity must be negative. So it's minus 10.159 because the direction of travel is down. Okay, that gives us the two velocities, so when we get to B, we know that we're moving with velocity 5 to the right and velocity 10.159 down. So if we draw a little diagram of what's going on at that point, right, we could see it's going like this. We're going 5 across and then much further down. Right, so this is 5, 10.159, and what we're looking for is the speed. The speed does not care for direction, it's a straight line speed, right, so it's the magnitude of the velocity. So that purple line there is going to be given to us by the square root of 5 squared plus 10.159 squared, and this is equal to whatever 103.2 plus 25 is, and then square rooted. Okay, 11.3 meters per second, and again that's to three significant figures as always. The final part of the question, part C, just asks you to find out the angle the velocity of the ball makes with the ground as the ball reaches B. Well, luckily I've already got my picture here, right? This is the ball reaching B, and this is the direction that it's travelling at. So if I've got B here, all we're going to do is look for the angle. So we can see the angle, right? This is the ground. The 5 is the ground, the horizontal distance. So we're looking for theta here. And hopefully we can see from this diagram that tan theta is equal to 10.159 over 5. So that gives me a value of theta of 10.159 divided by 5. Which gives me 63.8 degrees to three significant figures. And just be careful, we have to be a bit more descriptive. It does say that the angle the velocity makes with the ground as it reaches B, but let's put in that extra caveat that this is below the horizontal. Right, if we're describing a direction, let's always try and say if it's above or below as well. Right, 63.8 above the ground is a very different direction to 63.8 below the ground. Okay, that's the end of the lesson 6.3. That's really where the meat of the unit is for projectiles. It's always the same, right? There's a lot of key assumptions that don't change. It's using the Suvat equations and it's resolving it vertically and resolving it horizontally. There's loads of good problem solving questions to go out in this exercise. It's one of the really good exercises in mechanics. And it's of course exercise 6C. I would advise you to do the odds. Right, it is quite long, but obviously the exam questions are going to have a lot of problem solving elements in them, so that is good. You can see the E and the P questions to really have a go at to get you going with this once you've got a hang with the basics.